In episode 46, titled EDA Mindset, What You Look For Before You Model Anything, we focus on why exploratory data analysis is the quiet work that prevents expensive modeling mistakes and embarrassing conclusions.
Most failures in applied analytics do not come from choosing the wrong algorithm. They come from modeling too soon, before you understand what the data actually represents and what it can honestly support.
EDA is how you slow down just enough to avoid building a polished answer to the wrong question, or worse, a confident answer that is statistically neat but operationally false. The exam cares because EDA is not optional hygiene. It is part of causal and statistical reasoning, and it shows whether you can validate assumptions before trusting outputs. When you internalize this mindset, modeling becomes the end of a logical chain rather than the beginning of a guessing game.
Before we continue, a quick note. This audio course is a companion to the DataX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series.
A strong EDA pass begins by stating the question in plain language and then pinning down the target and the success measure you will use to judge whether you are making progress. The question should be specific enough that someone else could tell whether you answered it, and it should include the decision it informs, because analysis without a decision context drifts into trivia. The target is the variable you are trying to explain or predict, and in exam scenarios, it is often implied rather than explicitly labeled, so your job is to name it clearly and ensure it matches the question. The success measure is how you will evaluate quality, such as error size for regression, ranking quality for prioritization, or cost-weighted outcomes for rare event detection, and choosing it early prevents you from optimizing a metric that does not serve the goal. When you do this first, every later EDA check has a purpose because you are validating whether the data can answer the question you actually care about. Once the question is clear, identifying data types becomes the next practical safeguard, because type mistakes create summary mistakes, test selection mistakes, and interpretation mistakes. Numeric fields are not all interchangeable because some are counts, some are rates, some are bounded scores, and some are identifiers that look like numbers but behave like categories. Categorical fields include nominal labels and ordinal scales, and confusing those leads to treating arbitrary codes as if their differences were meaningful. Time-based fields add ordering and spacing, and that ordering changes what comparisons are legitimate, especially when time drives behavior or measurement changes. Censored outcomes are a special case because they represent partial information about event timing, and treating them like complete observations can flatten important risk dynamics. This classification step is not busywork. It is how you prevent the wrong summaries and the wrong tests from becoming the foundation of everything that follows.
Early in EDA, you should check record counts, duplicates, and missingness patterns, because these are the fastest ways to discover that the dataset is not what you think it is. Record counts tell you the scale of evidence, and they also reveal whether you have the expected unit of analysis, such as 1 row per user versus 1 row per event. Duplicates can be harmless, such as repeated exports, or they can be structural, such as multiple events per entity, and confusing those cases can distort rates and inflate apparent confidence. Missingness is rarely random in real systems, and the pattern of what is missing can reveal process issues, measurement gaps, or segmentation effects that matter to validity. A missing field might correlate with a specific region, device type, or workflow stage, which means naive deletion changes the population you are analyzing. If you find these issues early, you save time and you protect the credibility of anything you model later. Describing distributions in words is an underrated skill, and the exam often rewards it because it shows you understand what the numbers mean beyond a single average. Center tells you what is typical, but spread tells you how variable the process is and whether a single value represents much at all. Skew tells you whether extreme values are common on one side, which matters for choosing transformations, robust summaries, and appropriate statistical tests. Tails tell you about rare but important events, and in security and operational data, those tails often contain the most consequential outcomes. A field with heavy tails might make mean-based methods unstable, while a field with tight spread might be a strong signal if it shifts meaningfully by segment. When you can narrate center, spread, skew, and tails clearly, you are building an intuitive map of the dataset that will guide both feature engineering and interpretation. Unusual values deserve focused attention because they can represent either data quality problems or the most interesting cases in the dataset, and EDA is how you tell the difference. Outliers might come from unit mismatches, such as seconds versus milliseconds, or from parsing errors, such as truncated timestamps and malformed codes. They might also reflect legitimate rare events like incident spikes, unusual transaction bursts, or policy violations that matter disproportionately to risk. The exam expects you to recognize that blindly removing unusual values can erase the phenomenon you're trying to study, while blindly keeping them can let noise dominate your model. The disciplined approach is to ask whether the value is plausible given system behavior and measurement, and whether it clusters around known events, workflows, or segments. This is one of those moments where domain knowledge and careful reasoning matter more than any single statistical rule. Comparing groups is the next step because many modeling failures happen when a model assumes one population, but the data actually contains multiple distinct segments with different behaviors. Group comparisons can be based on geography, business unit, platform, device class, user tier, or any operational category that changes exposure and outcome mechanisms. Differences in baseline rates, distributions, or missingness across groups can reveal that a single global model will underperform, mislead, or produce unfair errors concentrated in one segment. Even when the goal is not prediction, group differences can confound simple analyses by mixing apples and oranges into a single summary. The exam often includes scenario details that hint at segmentation, and it expects you to notice when a similar overall average hides opposing patterns inside groups. When you compare groups early, you are effectively checking whether you need stratification, separate models, or at least segment-aware interpretation. Examining relationships between variables is where EDA starts to resemble causal thinking, because associations can hint at feature usefulness and also at confounding that will distort interpretation. Some relationships are purely predictive, meaning they help forecast the target but do not represent levers you can act on, and distinguishing those from causal candidates matters for how you communicate results. A strong correlation between two predictors can indicate redundancy and multicollinearity risk, while a surprising lack of relationship can indicate either no signal or a measurement issue. Relationships between predictors and outcomes can also reflect selection, such as when certain users are monitored more heavily, which creates apparent signals that are really artifacts of measurement intensity. The exam likes to test whether you will treat every strong association as meaningful, so the EDA habit is to ask what process could create the relationship and whether that process aligns with the question you are trying to answer. This is how you anticipate confounding and avoid building models that succeed on paper but fail in real decision contexts. Time ordering and seasonality deserve their own attention before you split data or evaluate performance, because time can quietly invalidate the assumptions behind common workflows. If the data contains trends, shifts, or periodic cycles, a random split can leak future information into training, inflate performance, and produce an overly optimistic view of how the model will behave in production.
Seasonality can reflect business cycles, user behavior patterns, operational schedules, or threat cycles, and those cycles can dominate signal in certain windows. Time ordering also matters because policies, products, and measurement systems change, and those changes can create discontinuities that look like effects if you are not careful.
The exam often tests awareness of temporal dependence by presenting a time-indexed dataset and asking what evaluation approach avoids leakage and misinterpretation.
If you notice time structure early, you choose validation methods and features that respect it rather than accidentally exploiting it.
After you understand structure and relationships, you can decide which fields need cleaning or standardization immediately, because some issues are so foundational that they should be corrected before deeper exploration. Standardization here includes consistent units, normalized formats, aligned categorical values, and unified timestamps, because inconsistent representations create false differences and hide real ones. Cleaning includes handling obvious parse errors, trimming invalid codes, and reconciling duplicates in a way that matches the unit of analysis you defined earlier. Some fields require normalization because they are measured on different scales, and while models can sometimes handle scale, EDA is where you detect whether scale differences are meaningful or accidental. The exam will sometimes describe data integrated from multiple sources, and the correct reasoning is to recognize that integration introduces schema drift and value drift that must be addressed before modeling. If you clean early, you avoid wasting time exploring patterns that are actually artifacts. Potential leakage fields should be flagged explicitly during EDA because leakage can make a model look brilliant while guaranteeing it will fail when deployed or evaluated honestly. Leakage occurs when a feature reveals the target indirectly, often because it is recorded after the outcome, derived from outcome processing, or encoded as a proxy for the label. In security data, a feature like case closed reason can leak whether an incident was confirmed, while in product data, a refund issued flag can leak churn outcomes. Leakage also occurs through data collection pathways, such as when only high-risk accounts receive certain monitoring fields, which can embed outcome-related selection into the predictors. The exam frequently tests this by offering a feature that is strongly predictive but temporally or logically downstream of the target, and the correct move is to reject it as leakage. ED is where you defend against this by checking how each field is generated and when it becomes available relative to the target. A high-quality EDA pass ends with a short findings narrative that guides the next steps, because analysis is not complete when you have plots or summaries. It is complete when you can explain what you learned and how it changes your plan. That narrative should state whether the data supports the original question, whether the target definition is stable and measurable, and what limitations or biases you discovered. It should note major data quality issues, key segment differences, and any time structure that affects evaluation or interpretation. It should also propose how modeling should proceed, such as which features look promising, which must be cleaned, which are risky due to leakage, and what validation approach matches the data's time ordering. The exam looks for this kind of synthesis because it reflects real competence, which is the ability to turn raw information into a defensible plan. When you can produce a concise narrative, you demonstrate that you are modeling with purpose rather than chasing patterns. A useful anchor memory for this mindset is understand, validate, explore, then model with purpose. Understand means you start from the question, the target, and the success measure so you know what you are trying to decide. Validate means you check counts, duplicates, missingness, and field generation so you trust the structure and know where it can deceive you. Explore means you describe distributions, outliers, group differences, relationships, and time structure so you can anticipate both signal and bias. Model with purpose means you only build models after you can justify why the data supports the task, why the features are appropriate, and why the evaluation is honest. The exam rewards this anchor because it stops you from jumping straight into algorithms, and it gives you a repeatable reasoning flow you can apply to many scenarios under time pressure. To conclude episode 46, imagine choosing one dataset story and narrating the EDA steps as a coherent sequence, because that is the best way to internalize the mindset. Suppose you are handed a dataset of user sessions and a target of account takeover events, and your goal is to estimate risk and improve prioritization without confusing detection artifacts with true behavior. You would begin by stating the question and success measure, then classify fields so identifiers are not treated as numeric signals and timestamps are respected as time-ordered evidence. You would verify row counts, duplicates, and missingness patterns to confirm the unit of analysis and to detect whether certain segments are systematically undermeasured. You would describe distributions, outliers, group differences, relationships, time effects, cleaning needs, and leakage risks in a short narrative that explains what you can model next and what assumptions you must keep in view, because that is how EDA turns data into decisions. Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.